Then, yes, there you go.
Yeah, and I don't have to click somewhere to it. Yeah,
No,
okay, great. Yeah, so I'd like to take the opportunity to talk about some of the things that that I think are very critical to our moving forward in terms of neuromechanics, which is muscle redundancy the fundamental problem of motor control? And what happens is that you often see this as the first line in essentially most papers. And it has served us well as a concept because the idea of how the brain controls the body is fundamental to understanding neuromuscular control, disease, rehabilitation. In the Netherlands, there's also a very strong tradition of sports sciences and performance, etc. So what I'd like to do is I'd like to revisit this concept of muscle redundancy, because the popular view is that we just have way too many muscles, right? Anybody who's eaten chicken will realize, like, there's so many muscles. I mean, what's going on here, right? So this allows for infinite solutions to produce a given net joint torque, right? So therefore, the conclusion is that the nervous system, or the inference that is now taken as a conclusion, is that the nervous system is faced with the problem, the computational problem of optimization, decision making. I have a million ways to do this. How do I choose it? And then, do I use energetics, etc.? And then the rest is history. Then the papers from 1970 on, that phrase is often attributed to Bernstein. So back in the 30s and 40s. So, but this is in a sense paradoxical with evolutionary biology and clinical reality, this idea of redundancy. There's a lot to talk about. I'll just give a very brief introduction so that I can jump into the more recent work that I'm doing. So for decades, neuroscientists have been exploring effective ways to choose specific solutions from the infinite set of possibilities. But if we really are so redundant, which muscle would you like to donate? This is a little bit tongue-in-cheek, right? But there could be an alternative evolutionary pathway where there would be another Francisco whose lineage has fewer muscles, needs to eat less, the computational problem is easier, etc. So you would imagine that evolution would have taken care of extra muscles. Now people say, well, so that you're redundant for, so that my grandchildren can potentially face a condition that I haven't faced and they'll do better. But this teleological thinking of robustness in the future doesn't work in biology, right? And then why do people seek clinical treatment for even mild pathology? Why are we so brittle in our rehabilitation? Or like, imagine an athlete, right? Do athletes use Botox to silence some muscles to improve their control? It's an interesting concept to explore and take to its logical conclusions, right? And so what I took as an approach at the time, actually, this is directly from Chow and Nance and Spore's work, who were starting to use linear programming back in the 80s, where you think of muscles as dimensions of control. So imagine that you have 3 muscles. So that means that you can activate muscle 1, muscle 2, and muscle 3 in different combinations, which actually paints a space. This is a graphical representation of the problem. And so imagine that you have 3 muscles acting on the arm. The activation of one of the muscles will actually produce, if the arm is fixed, it will produce a force in a given direction. That's mapped through the Jacobian and all those things that we know about moment arms, etc. But the point here that we're trying to make is that the set of all possible combinations of muscle forces, what we call a coordination pattern, is included in this space. This is a high dimensional space. And then what is it that determines what is a valid solution? You cannot just pick a point at random, right? It does something, but it might not be what you want to do. So how do we define the task? Well, in engineering, we would say that if I were to use every possible combination of muscle forces, I would get a variety of endpoint forces that you can do. But what if I wanted to produce a very specific force that is submaximal in a given direction of a given magnitude? Well, how do we define that? We define that by a constraint, right? You can say its horizontal magnitude is going to be that big. Well, what does that mean? If you actually roll out the mechanics in reverse, you see that there are the combinations of muscle forces with that particular horizontal component lie on a plane that intersects that volume. Now, but that doesn't fully define the task because it's only telling you the horizontal component. You say, well, how about its vertical component? Well, that's another plane. So therefore, by construction, the only coordination patterns that satisfy both constraints and are in the volume must lie in the intersection of all of these constraints, which actually defines a line. So what it means is that the feasible activation set is every point along that line. But if you're outside of that line, you're by definition, you're violating a constraint, so it's not producing the task that you want. So that's not a valid solution. Now, this is where we get a little bit into the semantics of redundancy. So these are all the possible ways in which you can do a task. And then one can ask, how many points are there on a line? They say, well, there's an infinite number of points, right? So it's true, there is redundancy. However, those points are not random. They're highly structured. And so defining that line, you can use it in parallel coordinates. You have to say, well, it's only the muscles that are activated at this level while the other muscle is activated at the other level, while the third muscle is activated at the other level. So there are these very highly structured correlations that just fall out of the mechanics. There's no brain involved here. It's like if you have a body with particular mechanics, number of muscles, the features of the task, that gives you the feasible activation set. So then it's only solutions inside that space that makes sense, right? And so you could actually say that there are solutions where muscle 2 and muscle 3 are silent because you see their ranges touch 0. So you could silence muscle 2, but you probably cannot silence muscle 2 and 3 at the same time. So that's one thing. So you could lose a muscle for that particular task, but you cannot lose the other muscle, or for a different task, maybe you cannot lose that muscle. But an interesting thing that happens here is that this muscle is never at 0, so it must always be active, for example. Another interesting thing that you can look at, is that a muscle has a maximal feasible value of activation. So if you overactivate that muscle, you would actually fall out of the solution space, which begins to explain issues of, say, spasticity in stroke or spinal cord injury, et cetera, that when your muscle is too active, you could also fall out of the solution space. So you have to have this particular correlation of activity among muscles. So this is work that we've been doing a little bit with ETH, et cetera, which is actually also a way to say that in my lab, I've had multiple master's and PhD students that come through the lab for a short stay that contributes to their PhD or their master. So I'd love to continue this type of work with your university. And so then we get into the computational aspects about how do you find those solutions. But without getting into details, if, say, this is a space that is embedded in a higher dimensional space, there are points in there. So actually only very recently, about 5 years ago, were we able to actually name all of the points inside of a, say, 7-dimensional space embedded in a 40-dimensional space. But you can actually list those points. And this is the work that Brian Cohn did. And so now there are efficient ways to sample. So you could use computational models to sample that space, et cetera. And so then what we do is Dr. Tulip, another Dutch, what he's saying is like, this is how biological systems work, right? You have tendons that are pulling on systems. So then what we then did is we started to ask the question, can I actually become the actuator of those tendons and understand the mechanics of how the neuromuscular system needs to work? And so we did some surgical work, cadaver studies, et cetera, with electrical motors pulling on tendons to understand the problem of motor control that the brain faces. So this in the center is Rod Hens, one of my mentors from Stanford. So then, there are many ways in which you can actually take experimentally a tabletop neuromechanical system like the hand, and then starts pulling on the tendons. And the purpose of this figure is to show you that from left to right, if your task is ill-defined, meaning you have few constraints, just push sideways with a certain magnitude. The structure is really not there. There are many solutions in the 7-dimensional space because it's a 7-muscle system. But if you begin to constrain the anterior-posterior direction of the vector and then the up and down direction of the vector, then you begin to see the structure emerging. Why? Because as you add more constraints, if there are valid solutions, the space would be in a lower dimensional subset of the whole situation. So this is one way to see 7 dimensions, right? And so the important thing here is that the structure is what is given by the mechanics. And a point that you hear me say over and over and over again is that it is within this structure that the controller can pick and choose, but only within that structure. So we call this now feasibility theory, but mathematically redundancy, of course, exists. There's no question about that. But what I am saying is that the solution space is very well defined, and any valid family of solutions must exhibit correlations, right? Because of the way the constraints of the task impose correlations. And so what we've done then is we've used this approach to reconcile the problem the brain faces. So what is it when we talk about neuromuscular control? What is it that we're really talking about? And how can we make progress? Because many of you are actively working in this area. So my hope is that some of these concepts will help you in your work. And so what I've done is I've structured this talk to sort of ask, given redundancy, given how it happens, given structure, the high dimensional problem, given a graphical interpretation of this problem, what problem is the brain solving from the mechanical perspective? Then we can ask the question, okay, if that's what's given by the mechanics, those are not the only constraints, because there are other constraints imposed by the physiology. And then once you have the mechanics and the physiology, you still have to learn how to use the system. So that's why I'm asking what mechanical, what neurophysiological, and what learning problems is it that the brain is really confronted with? And a lot of this comes out of the fact that mechanically, we are looking at tendon-driven systems, which are very different from the mathematics of torque-driven systems that we borrowed from robotics. The formulation that we use implicitly in a variety of computational models and platforms is that you need a net joint torque. And then once you have the torque, everything falls out. But how do you get that torque in the first place? So in the interest of time, I'm going to tell you the conclusions of this. So the mechanical problem that we're solving is an underdetermined problem. That's another way of saying redundant, but it's also overdetermined. And I'll talk a little bit into that. This is a little appreciated fact of mechanical systems that are driven by tendons, which actually have huge consequences. And then what neurophysiological problem? Well, muscles are not just, motors pulling on strings. They are afferented. They have reflexes. They have the gamma drive, etc. So that needs to be considered. And then the problem of learning that we're looking at is, now that we know that mechanically, because of the physics and the physiology, there is a subset of solutions, then the actual learning problem that the brain has is first finding, remembering and inhabiting that space of feasible solutions, and then explore that space and then exploit that space in a good enough way. So let me just start at the beginning. So like Hooper mentioned, This book is available. It's actually free to you because if you are a member of the Springer link, you can just download it for free. If you go to my website, valerolab.org fundamentals, all of my lectures are available there, all 27 hours if you so wish. And so one of the things that I did with Brian May, Bernd, Adeteja, is we took it a step further and say, well, that's the book, that's the material, right? But how does it relate to the state of the art, which I allude to in the book, but we worked it out. And in particular, something that you notice as a student coming into this field, and I'm trying to scroll here. So yes, I do see students here. The literature that you find in neuromuscular control is incredibly confusing. And it was confusing when we were starting to learn it. And now it's even more confusing because what you have are three distinct ways of thinking. And actually, they're not necessarily ways of thinking, but they tend to be more like cultures. They're the people who say, oh, optimization is the way. Tons of papers. Or people who say synergies is the way. Tons of papers. Other people say, well, there's probabilistic Bayesian, learning and approaches to motor control. And that's an entire field in and of itself. So my main goal today is for those students who are entering the field and would like to know, how do you make sense of this very complicated situation? Are they talking about the same thing? And most importantly, at some point in your career, you may think that you're being asked to become a member of one of these communities. But what I would like you to know is that that's not necessarily the case. So, in fact, in this paper, what we did is we said, okay, if we agree that there is a feasible activation set, and I don't know if you can see my my cursor. Yeah. Great. So here's a feasible activation set. So it's a lower dimensional object embedded in a high dimensional space. How many muscles do you have that you can control independently? Let's say 20. Well, you're in a 20-dimensional space, but the requirements of the task bring you down to, say, a 5-dimensional space embedded in 20 dimensions. So we know for a fact that that exists. That's just physics. That's moving from the bottom to the top, right? Physics and anatomy, etc. From the top, you have the motor commands that somehow need to send activation such that muscles inhabit that space at the level of, say, activation. Now, if you have, there is this legend of scientists in India, like 1,000 years ago, looking at an elephant, well, trying to identify an elephant in a dark room, and one of them would see the legs and say, "Oh, this is a tree." Another one would see, feel the tail and says, "Oh, this is a fly swatter." Another one would feel the trunk and say, "Oh, this is a snake." But it's really the elephant, just seen different ways. That's the same thing here. If you have a low-dimensional object embedded in a high-dimensional space, then it has a structure. So if you were to do PCA or NMF or ICA, of course it's going to be low-dimensional. Of course it's not going to be full dimensional, because otherwise there would be no task, no constraints. So when people were falling off their chairs saying, "Oh my God, if I record anything from a human and I do PCA, I get a reduction in dimensionality." Well, that is to be expected. Otherwise, you wouldn't be doing a specific task. You would just be, moving at random. Now people say, well, if I'm in this space and I want to find a particular location, well, you can find a cost function for which any point is an optimum for that cost function. So regardless of the optimization approach you use and the cost function that you prefer, so long as you're in that space, you're just moving around that space. And so you are free to pick the cost function that you prefer. Now, if you are looking at it from the probabilistic perspective, how do you sample? How do you do like a Markov chain or annealing inside of this space? How is it that you can sort of first find it and then move around in it, maybe do through trial and error, experience, etc.? Well, you build a prior of the space. Well, that you can call Bayesian. So all I'm saying to you is that the neuromechanics can be interpreted in these three ways, and they have. And now we have an unnecessary sort of separation among these perspectives. You, as students coming into this world, should not be bothered by the fact that there are three different schools of thought. You should pick and choose as needed for the problems that you're solving. You do not have to belong to any particular one. And then the other thing that we need to look at is not just the static situation, but how do you change that solution in time? So as you can imagine, as time goes by, the solution space changes because the Jacobian of my arm is different here than there. The forces I want to produce are higher here or lower there, whatever the task is. So this is actually a time varying space of solutions that then we need to navigate in time. So that's a paper that we're writing now with Brian and May. If there are any questions, please let me know. So to summarize this part, all the brain can do is identify and exploit the mechanical wherewithal of its body, right? And so the feasible activation set is the landscape upon which learning, adaptation, performance, and optimization, if any, must happen. And theories of motor control are simply different ways to describe these feasible activation sets. So this is gives you kind of a panorama of what you're looking at. In terms of why we're in this situation now conceptually, we borrowed from robotics the notion, like in every biomechanics course that we take or teach, you have a joint, you have multiple muscles, and you have a task, and you want a particular net joint torque. That means that you have forces from the muscles acting at a distance from the joint to get a net joint torque. Now, this is conceptualized as this equation where you have multiple forces acting across different moment arms that produce a single number, the net joint torque. So that's fine. Now, once you start moving, the situation is reversed. It's actually the transpose of the moment arm matrix, where you say that a single joint angle acting through the moment arms gives you different excursions of each of the tendons, right? So whereas the top one is an underdetermined system, you can find many solutions to give you one number. When you actually consider joint rotations, it's the furthest thing from redundant. And in fact, it's overdetermined. If there's a solution, there's at most one solution, which is that one joint angle determines the lengths of all muscles. And so if you take that into account, then movement production is not as redundant as we think, right? Because a given rotation, at least for the muscles that need to lengthen, those that can need to shorten, well, they can just go slack, right? But those that need to lengthen, they need to lengthen in a very prescribed way given by the moment arms. So well, there's no problem there, muscles lengthen. What's the catch there? Well, like Sherrington would say, inhibition is as important as excitation, right? Because what happens if even one of these muscles that's supposed to lengthen doesn't, for whatever reason? You say, well, if one of these in a single joint system, if one of those locks, then the system locks. However, in the multi-joint system, maybe the arm doesn't get locked up, but the movement would be disrupted. And the question is, what would disrupt that lengthening of a muscle? Well, we have stretch reflexes. So this brings us to the situation where we want to understand how is it that excursion is dependent on the behavior, and the velocity with which a muscle lengthens is very important, because the faster that you lengthen a muscle, the stronger will the stretch reflex be, right? So Dan Hagen, one of my students, he was very interested in basketball. So And I was asking him, so Dan, can you tell me, so I see a lot of you here, so I'd like to see if anybody would raise their hand. Who gets paid $1 million a game to throw a ball? Let's see. I don't see anyone who gets paid $1 million or €1 million. And so if you're looking at a basketball game, why is the free throw even interesting? These people get paid, what, $1 million a game. They've been doing this all their lives, at least 10,000 hours. They know how to throw a ball. Why is it even a question whether or not they'll score? Right? So Dan started looking at this problem and he said, well, you know, what does it mean to score? Well, that means that you release the ball at a given point with a given angle, with a given velocity. The rest is history because it's a ballistic movement. So how many ways are there of taking your hand from a starting position to the throwing position, start and end at the same place with the same initial projectile velocity? So this is a 2-point boundary value problem, right? But we looked at it strictly from the kinematic perspective. So what Dan did is he found 100,000 ways to go from here to there and end with those particular boundary conditions. With, I believe there were 18 muscles. So he went into the literature, he found all the moment arms across the movements, etc. And so what he found was here, this blob is 100,000 solutions, right? But let's look at 3 solutions that look pretty similar. It's a planar model, just to make the point, right? You start here, you end there. You know, these are trajectories 1, 2, and 3. If you look at trajectory 1, 2, and 3, then you also look at 1, 2, and 3 in terms of angle, angle, angle plots. The angle at the wrist, the angle at the elbow, and the angle at the shoulder. Now, if the angles are different, then the angular velocities are also different. So then for each of these 3 example solutions, the eccentric and concentric velocities of the muscles are different. They're not identical. And the question is, how different are they? So what we did is we showed that these 3 trajectories that look very similar from the perspective of the endpoint actually have eccentric contraction velocities that can be almost an order of magnitude apart. And what does this mean? It means that if you must time not only the drive to the muscle, but also the shaping of the reflexes, in one case, you have to do this 10 times better than the other case. So probably the role of the coach is to have you operate here in this particular realm of kinematics, because it's more forgiving to potential errors in your activation contraction dynamics, potential errors in the reflexes, etc. So this is kind of a consequence of the system being over-determined, where few joint angles determine the lengths and velocities of all muscles. And so I've already been hinting at the neurophysiological problem of reflexes. So before I go there, are there any quick questions, clarifications? Okay, then we'll proceed. I don't see all of you, so if you unmute and say something, I'll know. But so then we'll proceed. So that was kind of the mechanical problem of tendon-driven systems. How must you solve that problem? The next question is, what neurophysiological problem does the brain solve? Well, from the neurophysiology, this is taken from a paper by Jerry Loeb here at USC, where there's a long, long tradition of mapping out how a muscle is activated. The version of this that we use in biomechanics is to say that there is an alpha motor neuron excitation to the bulk of the muscle. And that is, of course, perfectly correct. However, muscles have sensors. They have Golgi tendon organs, they have muscle spindles, one thing. The other thing is that muscles have interconnections among them. You have anything from the 1A interneurons to the Renshaw cells, etc. So every muscle is actually wired up with every other muscle or many other muscles in the same and other limbs, and then things cross over from one side of the body to the other. So it's kind of a complicated circuit diagram. But as a first step, what we were looking at was in addition to the alpha drive to the muscle, there's this thing called the gamma drive, which is the tuning of the stretch reflex. So if you do that, so if you look at that for a single muscle, you have in red the signal from the motor cortex that goes to the alpha motor neurons and drives the bulk of the muscle. Then you have the muscle spindle that is sensing in a tunable way the length and the velocity of the fibers in the muscle. Those project back to the alpha motor neurons, and they cause the stretch reflex, which is what gives you muscle tone. However, the muscle spindle is sitting in some other muscle fibers called the intrafusal fibers that are driven by a separate motor neuron called the gamma motor neuron, which is controlled by the motor cortex, but also by brainstem and reticulospinal pathways, etc. So it kind of gets very complicated there. But we've known this since 1896, actually, not sooner. So the idea that we are coming up with here in the lab, and we're working actively on this, it's like, what is an afferented muscle? By afferented, we mean a muscle that also sends sensory signals back to the spinal cord that are then used to modulate its activity, which is thought to be, very much at the root of issues like Parkinson's disease, spasticity, stroke, etc. I mean, when the gamma system or the fusomotor system is disrupted, bad things happen. And so Richard Feynman, a physicist, once said this about mathematics, right? What I cannot create, I do not understand. So then we took a very naive approach to this and said, do we know what muscles are? Do we know what tendons are? Do we know what the particular circuitry in the spinal cord is? Well, we should be able to build one. So then we took it upon ourselves to create a synthetic spinal cord that drives motors that behave like muscles that then act on a hand, because it's a tabletop system. And so for this, I've assembled a large team of students and faculty from a variety of dimensions, anything from neuroscience to neuromorphic computing to electrical engineering, et cetera. And so what we're doing is we've created these sort of simplified, ultra simplified spinal cords on a chip, where we have FPGAs, field programmable gate arrays, that are programmed to behave like spiking neurons, like simple neurons. Izikevich has done that. It's like a simplified version of the Hodgkin-Huxley, integrate and fire dynamics. So, but then you have this in a way where we have, in blue, we have the physical world. This is not in simulation. This is an actual physical system that you get, for which you get, say, the lengths of the muscles. They go into a spindle model. Then they go into a model of the size principle of the spinal cord. Then they go into a model of muscle activation. Then it goes into the motors. The motors create the currents, are given the currents to produce a force that then acts on the physical system, and then round and round it goes. And so I hope you can see the movie here. So what it is here's just a stick with two motors, but you have these simplified spinal cords with 128 spindles, 768 motor neurons per muscle, very simplified hill-type models. But the interesting thing is that you just turn it on. You just turn it on, and you have a robot with muscle tone. It has stretch reflex. And this is actually a very hard problem in robotics we can get into. And there's no need for negative gains here in a fast 10 millisecond inner loop. This is just a dumb system that is the implementation of the very first chapter of any book on spinal neurophysiology. And the thing is that you can drop electrodes, you can record from any one of these neurons that are being simulated, And you can hear the stretch reflex, right? So what we're doing is we're saying, well, if we really understand sensorimotor neuroscience at that fundamental peripheral level, by peripheral, I also include the spinal cord, then we should be able to test our theories of motor control. And so here is what we're here replicating work by Edin and Valbo, where they were actually recording spindle systems while people were put in a contraption that would move their index finger back and forth. So we repeated that experiment with a real cadaver hand. Let me just show you this. This is a cadaver hand, actually, because we wanted to get the mechanics right. We didn't want to say, oh yeah, a joint rotates and you get this moment arm and this stretch in the tendon. We didn't want to assume anything. We just said, okay, what would it work like on the real system? And here, this looks like a paper from the Journal of Neurophysiology, where you have the 1A and 2 spindle firing rates, where you have the rasters of recruitment and rate coding at the alpha motor neuron levels. Then the model produces the EMG that you would record, and then the force that you would see at the muscle and the actual force that was measured at the tendon. But this is all synthetic, right? So this is the ugliness or beauty of a system that has the very fundamental wiring of a muscle. That is what then needs to be controlled by the body. And it's not pretty, right? So how is it that the brain is dealing with all these things is the question. And here we then ask a very simple question. How can I move my finger back and forth? The simplest voluntary task, because what I showed you before were on involuntary reflex responses or just maintenance of muscle tone. But here I'm saying, okay, what if I had volleys of agonist and antagonist alpha signals going to a finger so it goes back and forth? Because the question is, how do you regulate the gamma system? It's actually one of those mysteries in physiology that we know the gamma system is there. We know it exists. It's very difficult to record from it. And on top of that, it's been attributed to be the source of a variety of neurological conditions, but we've never really tried it out. So what we're doing here is we're asking what happens if you lead or lag your gamma system with respect to the voluntary drive. And so what you see in the next movie is how we actually were able to explore the slew, as it's called, or the lead or lag of the gamma system with respect to the alpha motor neuron system. And what you see is that in yellow, you have a region of maximal finger excursion, meaning if you do, for the same agonist-antagonist drive, if you don't time the gamma system to the spindle in the right way, you actually get no movement. But if you combine them in a particular way, then you get movement. So perhaps this is actually what the brain is learning. How do you learn to move voluntarily without disruptions? And this is the first time we created quote unquote voluntary movement of simple back and forth movement, flexion extension. And you notice that that movement doesn't look right. I mean, it looks okay. But if you were to see this in a clinic, you'd be saying, okay, maybe you have a touch, maybe you had a slight stroke, or maybe your deep brain stimulation is not set right, whatever, but you can tell that it's not smooth, right? And so the nice thing about this is that our bugs could be a pathological condition, right? If, of course, we can have bugs that are just bad, right? Just bad engineering, but it could be that by setting the parameters incorrectly, you're actually exploring the emergence of pathology. And here we have the very interesting premise that the presentation of pathology in humans is actually a consequence of the way systems are controlled, of the hierarchical distributed circuits of reflexes and muscle properties and intermuscle connections, etc. And then the last part, in the last 10 minutes, now that we know that there's a mechanical problem the brain needs to solve, and then there's a physiological problem of afferentation that the brain needs to solve is, well, how do we even learn? How do we learn so quickly? Especially in a dynamical situation where you want to explore ways in which you can learn to move in a particular way, the way the brain does it. So there are many ways to approach this, and you're all familiar with work in optimal control as one of the many control strategies, because you could use simulated annealing, you could use just PID control, you could use formal, Bryson style optimal control to have a dynamical solution to the problem of movement. That's what a lot of our literature is about, right? But what we wanted to do is not solve this like engineers. What we wanted to say is, if we put ourselves in the shoes of a biological system, how can we come up with something that's biologically and developmentally plausible when learning to control a tendon-driven system in hardware, not in simulation, so that you get all the ugliness of friction and stiction and impact, etc., and in real time, meaning that it should be controlled as an animal. When it's born, it learns to move by itself, and it doesn't have time to read all our papers. How would it do it? And so we have this project with DARPA where we want to create autonomous functional movements in the tendon-driven leg via limited experience. And what we wanted to do is I was very mean to my students. I said to them, it has to be few-shot learning. Few-shot is one of the terms, one of the jargons that's coming up that's opposed to traditional deep learning. In deep learning, you have all the data in the world. Here, you have only a few bits of data. It's incomplete information, because when an animal is born, it doesn't have the benefit of somebody else's experience. It can only learn in its own body. It has to be autonomous. It has to be in hardware, not with a clean physics that we can have in simulation. It has to be adaptable and robust. It has to be driving a tendon-driven system. It has to have the nonlinear hybrid dynamics of braking and making contact, like for locomotion. And it has to be solving this problem of over and under determined, right? Because it has to be dealing with back drivable motors. Here, we didn't add the layer of the spinal system. We just added, we have brushed DC motors that you can fight and unwind if you wanted to, if you pull hard enough, which is a simulation of an afferented muscle. And they should be able to do multiple tasks. And so actually, this algorithm is called G2P, general to particular. It actually learns to learn. It has to be agnostic to the task. And so the leg that we created, or we're now doing this with fingers, but in this particular case, we have a leg, 3 tendons, 2 joints, and we made a little treadmill that it was meant to sort of push back as it was simulating the gait. And here's a movie about how it learns. So here's like an ugly floppy system, right? So it's just the physics. And then we gave it 5 minutes of babbling. We just gave it random step changes in the current to the different muscles, and we recorded the joint angles here. So what we're doing is we're collecting the input-output data. This is an end-to-end machine learning system where we have a few data points, then we invert that to create a bad inverse model of the dynamics. And then what the algorithm does is it actually shapes the current to the motors in a way that can produce a different new behavior every time it runs. It's like trial and error learning, right? And so among these solutions that you find, and I can play this video later on, but you find that there are some good solutions and there are some bad solutions. And also, there is no explicit model of the system. It's all data-driven. And then you could also see here that repetition, just familiarity with the task, improves the task itself, which starts to sound a lot like biological systems, right? And then the reviewers were asking us, well, how about perturbations? Maybe you're just manufacturing these tasks. And so then my students just went ahead. They were so surprised when they just whacked it and it kept going. So, and then the reviewer said, yeah, but what about point-to-point movements? Well, you're not actually implementing necessarily a limit cycle as you would in some other dynamical solutions to this. And how about just like a crazy dance? So you can also combine cyclical with endpoint solutions and stuff like that. So then there's a lot to talk about here, but getting back to our original question, if here we have our new quote unquote tendon-driven approximated neuromechanical system, and you wanted to produce gait that pushes this treadmill backwards, what is it that we're really doing? What we're really doing is we're finding a time history of a path in three-dimensional space of currents. Current to motor 1, motor 2, motor 3. And what you want to find are the correlated, because they have to be correlated, the correlated activations among the currents to the three motors that will produce the task that you're looking for. So if you were to do PCA on this, of course, you'd see it's a two-dimensional thing. In fact, if you do proper nonlinear dimensionality reduction, you would see that it's a single degree of freedom closed orbit, right? And so one of the things that I ask my students to do is like, okay, let's see the currents live. So we had, current sensing resistors that we put in there. And what I'm going to show you now are the evolution of two different cases, where in red, you see the first 3 attempts, and in green, you see the last 3 out of 24 attempts. So let's see here. Let's see. Here we go. So here you see the first 3 and the last 3. Of course, the last 3 are sort of cleaner, but the first 3, as you see, actually the system fighting itself. Much like, when people are learning a new task or exploring a solution or learning to move, you're just fighting yourself, you get too tired, etc. But eventually you find a way to do these kinds of dynamical tasks properly. So I can talk in detail later on about how the algorithm works. It's published. You can get it from GitHub. To help you find it useful. It's out there. But the idea here is that it takes 5 minutes of learning. You get a bad inverse model, and you actually look for good enough solutions that then produce motor habits that may or may not be optimal. Because optimality, in my opinion, is highly overrated. Oftentimes, optimality is used as a methodological step because it helps us solve problems, but it doesn't mean that biological systems are necessarily optimizing at that level in that way. But it also shows the emergence of motor habits. So here's another interesting corollary of this, is that the way I move, the way I behave, the way I talk, etc., is a product of my own experience. So my experience drives my learning. It gives me a motor habit, and it's who I am. If I want to shape that behavior, I could, quit my job and become an Olympic athlete and devote all of my time to training my basketball free throw so that I make $1 million. But in the absence of that experience, well, I can just move in a good enough way. And then the way I move is idiosyncratic. It's a habit I have. And people have motor habits all the time. And so here you could see the evolution of a variety of different runs for the same system. We have an exploitation phases, and then they evolve, and then they improve, they find a solution. And the one thing I wanted to show you is this, pretty much close to the last slide, is that if you look at the energy consumed in each of these runs, that gave you these different motor habits, because each solution ends up being a motor habit where the big dot is the one with the highest performance. Now, the triangle is where you started, and the big dot is where you ended. And you see that you always end at the highest point of this exploration of the solution space. But interestingly enough, energetic cost in watts is on the horizontal axis. We wanted to know if efficiency was kind of sort of falling out of this situation by itself. We didn't force it. We just asked, and it's not. Meaning that the best solution is not necessarily the one that leans to the left as being the less costly, because you could have solutions that are costlier, but they're better. And if you can just do the job, you can of course optimize later if you so wish, but it's not a prerequisite for finding a solution. So now, hopefully this makes a little bit more sense. Now the mechanical problem that we're solving is the one of under and over determined mechanical tendon-driven systems that are driven by afferented muscles with the need to consider all of the neurophysiology behind what a muscle is. And the learning problem is one of finding, remembering, inhabiting, exploring, and exploiting a solution manifold in a good enough way. And so we call this a neurosharing-Tonian neuromorphic approach because we wanted to confront the same tendon-driven control problem the brain faces. And then this allows us to put our theories of neurocontrol to the ultimate test of physical implementation. So we're building robots that are supposed to be solving the problem that we think biological systems are solving. And then we can develop testable hypotheses of motor control, motor learning. And in so doing, you could also have a lot of fun revolutionizing robotics and prosthetics in a way that is bio-inspired. And with that, I'd like to thank the many people in the lab. I've been mentioning some of them here and there. We have some more recent papers and of course our funding sources, and you for your attention. Thank you so much.
Thank you very much, Francisco, for this very inspiring talk. And nice coherent study, for a coherent presentation. At least one thing I took from it is that you voluntarily not earn $1 million, but
yes, I left that on the table. Yes, I love science that much.
I wasn't aware of that. I was doing the same thing, but we have well, it's 5 o'clock, but I think we should have some time for questions before we move to the social in Wonder Me. So please unmute yourself and ask your question to Francisco.
And I'll leave the slides on in case we want to go back to one of them.
Yeah, Francisco, Martin speaking. Thanks
Hey,
for
Martin.
a very inspiring talk. But just out of curiosity, why are you looking at physical implementations rather than using computer modeling?
Well, that's a very good question, Martin, because as you know, I think of myself as a modeler from the beginning, right? I started doing models. Mm-hmm. You know, you also do modeling. A lot of my best friends do modeling. And modeling can be very good. So, however, in the case of the hand, like who can tell you, I'm sorry to say, we still don't have a model that takes into account the squishiness, the hysteresis, the linearities of the problem. So I think models have their place, of course. Half of my career is in making arguments on the basis of models. But also there is this idea of synthetic analysis, which is, I mean, models you can see as an extension of analytical work. But synthetic analysis is one of putting things together and then dealing with the beautiful physics of the world as they exist. For example, some of the things that we found were that tendons have minute changes in how they're stretched, and that actually affects the spindle signals. And then the spindle signals are then uglier than we would think. And we wouldn't have seen that had we just used a model with a very nice hook relationship for the tendon. And then we would be thinking that the spindle was solving a different problem than it really is. So now we're actually confronted with the issue of something that's actually been studied in some systems, like, is there pre-processing of afferent signals to clean or extract the noise or whatnot, or is it really noise, or how is this true spindle signal really sensed, because it has consequences? So that's just one example of that. And the other thing is that it can take us into the wonderful world of robotics.
Yes, I understand that.
And
Which is always a lot of fun.
wearable.
It's more convincing to show somebody
Yeah.
something that moves. And
But imagine being able to have exoskeletons that are driven by these particular bio-inspired neuromorphic controllers, so robots that yield, or braces that yield with you, and things like that. Yeah.
cool.
Hi.
Thanks.
Hi, my name is Suraj. I'm one of Dr. ValeroCuevas' students. I just like to add another important thing. I mean, at the lab, we're now working on more learning algorithms. Consider this: when you're in simulation, you have the luxury of being able to accelerate using GPUs and learn at hypertime, where you can have 20,000, 50,000, 100,000 epochs of the same kind of technique to learn a very specific task. But as was highlighted with G2P, we don't have that luxury. We need to learn, we need to explore and exploit at the same time, which means we have to very quickly learn. That's just another reason.
Okay, thanks.
More questions?
I have a question, if I may. Hi, Francisco. Jaap van Dien here. Thanks for your presentation, first of all. If I understood correctly, in the learning experiment that you showed, you leave out the problem of the afferented muscle. And I was, if that's correct, I was wondering to what extent that would, let's say, mess up the few shot learning.
Well, that's exactly what Suraj can talk to you about at the informal meeting. That's the topic of his PhD. Now that we've been able to do the end-to-end learning, the question is, how does such a few shot learning approach handle that extra layer of, I mean, I hesitate to use the word complexity, because it might not be complex. Somehow in biological systems, you co-evolved the physiology with the mechanics with the learning. So my sense is that it's not useful to inherit a body from your parents that you cannot learn to use quickly. And we all inherited bodies with this middleware, this middle layer of afferentation. So it's probably a situation where you have many good enough solutions. You just find one and then you stick with it. So I'm very, very curious to see what Suraj's last chapter of his dissertation is going to be about. You know, as you, and even in the spinal, like, as you begin to add more interneurons or the differential cells, etc., is the problem simplified or not? Because to the engineering thinking, we might be saying we're complicating it, but like Hug knows very well, the properties of muscle are immensely helpful. They are a form of embedded logic. They actually solve a low-level control problem that then the brain doesn't need to solve. And so we'll see. It's exciting times.
Thanks.
Who else has a question?
I'm particularly interested to hear from the students to see if it's helping them sort of navigate this this very, what is now, I think, become a very confusing literature where there are definite camps, right? If you go to a synergy session, you talk about, Bayesian, and they'll kick you right out, right? Or if you go to an optimization session and you say, well, why are you using a quadratic cost function? You'll get kicked out of the room, right? So nicely, of course, but
well, there are some people that do synergy analysis in this room. I'm not sure whether they have some thoughts about this. I actually, someone going to respond, or shall I ask my question? Also, one of the things that I've been interested in is also the sensory feedback and the
yes.
well, if I would still call it the complexity or the wealth of sensory information that is sent to our central nervous system. And I noticed that in one of your models, you actually do include a lot of muscle spindles.
Yes.
And so one of the, I think, still unsolved questions is, why do we have so many? And is this something that could be addressed with the current models you have?
Well, that's a very good question, where actually Jerry Loeb has worked a lot on this issue about muscle spindles. And there's a beautiful paper from 1974, I believe, where they actually count muscle spindles per gram of muscle throughout the body, right? And you get some interesting situations where we think that the spindle count is proportional to its utility as a sensor. And in fact, there was a time when people were thinking of the lumbrical muscle, which we know and love, right? Lumbrical muscle is like the smallest of muscles, and it actually doesn't go from bone to bone, it goes from tendon to tendon. And people thought, well, maybe it's not a muscle after all, it's just there to house the spindles and be informative, but it's not particularly well populated by muscle spindles. So what we're doing is we are creating a modular system where a muscle has an associate number of muscle spindles as a module. Because a motor unit, you can think of a motor unit in the motor sense, the alpha motor neuron and the fibers it innervates. But then those fibers have to project back to that same alpha motor neurons through the spindle system. So if nature has modules, we will have modules too. And so we are, in a sense, obliged to have as many spindles as there are motor units, just because that's how the system's wired. And is it a bug or a feature? I don't know. And then we actually have a recent paper that's in review now, where we say that muscle spindles alone cannot be used to control movement, that the Golgi tendon organ is essential for that. It kind of, in a bioinformatic way, that there's this very interesting relationship between muscle spindles and Golgi tendon organs, and why did we evolve to have both, etc. So a lot of open questions.
Okay. All right, maybe one more chance for other people to ask questions. If not, then we'll go to...
And also, if people want to come and spend a semester in the lab, we've done that many times. We welcome that with ETH and Innsbruck and London, things like that. So
any postdoc positions you have?
Yeah, I might. So if people are interested in this, but yeah, I do look forward to visiting you in person sometime soon. Yes. And I really appreciate your time. I know you need to get home, or maybe you're already home, but you need to get back to your beautiful spring. That things are blooming now. So thank you for having us.
Yeah, thank you very much. Well, we will continue our meeting in Monami, and if
I'll see you over there.
Would like to do that as well, then they're free to.
Great.
And But thank you for this presentation,
No,
Francisco.
thank you. Thank you.